What problem does the proposed COPE method aim to solve in the context of position encoding in large language models, LLMs?
The proposed COPE method aims to solve the problem of integrating context and position addressing together in the context of position encoding in large language models, LLMs. Traditional position encoding methods, such as absolute and relative PE, treat position and context addressing independently, leading to limitations in tasks that require nuanced understanding of sequences, such as counting problems and selective copying tasks. COPE addresses this issue by introducing a new position encoding mechanism that measures positions in a context-dependent manner, allowing the model to represent various levels of position abstraction simultaneously, from token positions to sentence positions. By incorporating context vectors to determine which tokens to count and using gate values to compute relative positions with respect to the current token, COPE enables the model to attend to specific tokens based on their context and position, leading to improved performance on tasks that require complex attention mechanisms over ordered sequences.
How does the proposed method COPE work and integrate context and position addressing together? Illustrate step by step.
The proposed method COPE integrates context and position addressing together by first determining which tokens to include in measuring distance based on their context vectors. This is done by computing a gate value for each query vector vec, q_i and key vector vec, k_j pair where j less than I. The gate value is determined using a sigmoid function, where a value of 1 means the key will be included in the position measurement, while 0 means it will be ignored. The gates are conditioned on the query, allowing for different position measurements for each query if needed. Next, position values are computed by adding the gate values between the current and target token. If the gates are always 1, then the position value p_ij is calculated as I, j plus 1, essentially recovering token-based relative positions. However, in general, p_ij can represent counts of specific words, word types, number of sentences, or other concepts useful for the transformer during training. Unlike token positions, the position values in COPE are not restricted to integers and can take fractional values due to the sigmoid function. This means that interpolation between integer values is used to compute position embeddings. These position embeddings are then used in the attention operation, allowing the model to measure distances in multiple units simultaneously. The contextual position values can vary from query to query and layer to layer, enabling the model to capture various levels of position abstraction, from token positions to sentence positions, all while considering the context of the tokens being processed.
What are the theoretical or practical benefits of using COPE method over existing position encoding methods, such as absolute and relative PE?
The theoretical benefits of using the COPE method over existing position encoding methods, such as absolute and relative PE, lie in its ability to measure position in a context-dependent manner. COPE integrates context and position addressing together, allowing for more complex attention mechanisms that can attend to specific tokens based on their context and position within the sequence. This contextual position encoding enables the model to represent various levels of position abstraction simultaneously, from token positions to sentence positions. Unlike token-based positions, COPE's position values are not restricted to integers and can take fractional values, providing a more nuanced and flexible way of encoding position information. Additionally, COPE allows for better generalization to out-of-domain tasks by incorporating counts of specific tokens into positional embeddings, enabling the model to attend to the last-seen positions of tokens more effectively. In practical terms, COPE has shown superior performance in tasks such as the flip-flop task, selective copy task, counting task, language modeling, and code modeling, outperforming existing methods and demonstrating improved generalization capabilities, especially in scenarios with longer context sizes.
How was the proposed COPE method validated or tested in the paper?
The proposed COPE method was validated and tested in the paper through several experiments on various tasks. Firstly, COPE was applied to toy tasks such as counting, selective copying, and the flip-flop task, where it outperformed token-based PE methods, especially in out-of-domain generalization scenarios. Secondly, COPE was tested on a language modeling task using Wikipedia text, demonstrating improved performance compared to standard PE methods. Additionally, COPE was evaluated on a code modeling task, showing a 17% improvement in perplexity over absolute PE and a 5% improvement over rope. Furthermore, a new word count task was introduced to assess COPE's effectiveness in counting specific words in sentences, where COPE significantly enhanced the model's performance on this context-dependent task. Overall, the experiments across different tasks showcased the superiority of COPE in handling position encoding in a context-dependent manner, leading to improved model performance and generalization capabilities.
What results were achieved with the COPE method in toy tasks and real-world applicability like language modeling on Wikipedia text and code training?
In toy tasks such as counting, selective copying, and the flip-flop task, the COPE method outperformed existing token-based position encoding methods, especially in out-of-domain generalization scenarios. In real-world applicability, when tested on a language modeling task using Wikipedia text and code training, COPE also led to better performance compared to traditional position encoding methods. Specifically, in the language modeling task on Wikipedia text, COPE outperformed relative position encoding and further improved performance when combined with relative position encoding. In code training, COPE embeddings improved perplexity over absolute position encoding and rope by 17% and 5% respectively, showcasing its effectiveness in structured data like code. Additionally, in a new word count task where the model had to count specific words in sentences, COPE significantly improved the model's performance on this complex context-dependent task. Overall, COPE consistently demonstrated superior performance in both toy tasks and real-world applications, highlighting its effectiveness in various scenarios.
What are the limitations or drawbacks of the COPE method proposed in the paper?
The limitations or drawbacks of the COPE method proposed in the paper include the extra computational cost associated with computing and storing vectors vec, EP_ij, which requires additional compute and memory. Additionally, the method may face challenges in scenarios where the gates are sparsely activated, as it may struggle to cover the entire context T with fewer positions. Another limitation is that COPE may not generalize well to longer context sizes, as tokens outside the training span of T may not have position embeddings added to them, negatively impacting performance. Furthermore, while COPE outperforms existing methods in various tasks, there may still be scenarios where it does not provide significant improvements or where other methods may perform better. Lastly, the method's effectiveness may depend on the specific hyperparameters chosen, and certain choices may lead to degradation in out-of-distribution generalization on certain tasks.